We've got our second midterm coming up on Tuesday, and today's lecture will be included. So you can see we've got quite a few topics, but I don't think I'm going to get through most of them, or at least all of them. So if you want to make it slower today, you can ask a lot of questions. That way you'll have less topics to cover in the midterm. Okay. Good strategy. So let's continue from where we left off in the last lecture. We were talking about shortest path algorithms. And the way I'm going to do this particular lecture and the next one is a little different from the order in which topics are typically covered, for example, in the book or perhaps other instructors. What I'm going to start off is by looking at some of the common some of the common procedures that are going to be used in two of the major algorithms that we're going to look at for shortest path. And these are both Dijkstra as well as Bellman-Ford. So the initialization and relaxation procedures are going to be common to both of these algorithms. We'll take a look at these. Then we'll take a quick look at the two algorithms, try to understand them at a relatively high level, and do their analysis, which is generally the easy part. The proof of correctness is a little tricky for both of them, all right? But we will spend time doing the proof of correctness for both Dijkstra as well as Bellman-Ford. And before we do the proof of correctness, we need to be able to understand a whole bunch of properties about the relaxation procedure in particular, okay? So I'm not sure to what extent I'm going to get through this part today, but I hope to at least be able to cover the basics of the two algorithms, both Dijkstra as well as Bellman-Ford. Right, so let's do a quick review of some of the things we spoke about in the last lecture. We spoke about the general single source shortest path algorithm, and we defined WP as the weight for a particular path, which is simply the sum over all the individual weights of that particular path. We then defined the shortest path weight. So delta is the shortest path weight, okay, between any two pair of nodes, U and V. So assuming that somehow you've got a magic wand and you can figure out what the shortest path is, then that is what delta is, okay, as opposed to the weight. All right. So the weight could be, it doesn't necessarily have to be the shortest path, but delta will presume that you've somehow found the shortest path and it's the weight of that particular path, okay, which is how we define it over here. And if it is not reachable, then the shortest path weight is infinity. And then, as I said last time, you could have multiple shortest paths, and for any one of those paths, we will obviously have the case that the weight of that particular path is equal to the shortest path weight delta. Okay, and that could happen to multiple cases, as we saw in the previous lecture. And then we looked at various variants of the shortest path, and I'm not going to go over that again. And we also saw the issue of negative weights. Okay, so this is going to become relevant again when we look at Dijkstra's algorithm, as well as Bellman-Ford. So let's take a look at the common initialization procedures. So we went over some of it in the last lecture, and we said, well, first thing that all these algorithms, and this is not just true for the two of these, there are more algorithms as well for shortest path, and all of them have these common initialization procedures. So initially what we're going to do is we're going to define V dot D to be a shortest path estimate, okay? So that is different from the delta function, which was the shortest path weight. Okay, so initially, all of these algorithms are going to try to estimate the shortest path weight, and then they're hopefully going to go through a series of iterations by which they will reduce the value of VD, and initially it's going to be set to infinity, and slowly you're going to come down to a level where ultimately it's going to be equal to the shortest path weight. Okay, and once it reaches that particular value, then presumably the algorithm is done. Okay, so at the conclusion of all of these algorithms, we hope that the estimate is actually equal to the shortest path weight. The shortest path tree will essentially will comprise of the edges. Okay, so going from v to v dot pi, which is the predecessor, those will essentially comprise the shortest path. Okay, and we saw how it resembles Prim's algorithm last time as well. So let's next take a look at the next initialization process, part of the initialization, which is a common procedure which you'll see across the different algorithms. And this is called relaxing an edge. Okay, so what does that mean? It's a fairly simple concept, but as we go through proofs, it can become tricky. So it's important to be able to understand it appropriately. So it basically says that if we have a particular source and we have two edges in a graph, so you have u and v, all right, and we already have estimates. Okay, so we have a shortest path estimate for both of these. So we have the shortest path estimate. By the way, d refers to distance. So I don't know why it's referred to d. Could have called it u dot e, would have been the better appropriate nomenclature for estimate, but we call it u dot d. Okay, so u dot d essentially is the current estimate, and v dot d is the current estimate to go from s to v. Okay, so given u dot d, the current estimate to get to u, the v dot d, the current estimate to get to v, and given the weight between u and v, the single edge between u and v, so the question that we're asking is that, can we find a better path to, can the shortest path estimate v dot d from s to v be improved by going through the particular edge? Okay, yes. Yeah. Right. So that's perfectly said, and it's a fairly simple concept. I mean, all you're saying is that we already have an estimate to get to u. We have an estimate to get to v, and we know what the cost is from u to v. Right. So if u dot d plus this particular edge weight is added together and is less than the current estimate to get to v, then you simply replace it. That's the whole concept of relaxation. Okay, so at the surface, it seems to be a very simple concept, but as we go forward, you will see that as it applies to a particular graph and you're trying to do proofs, it becomes important as to understand it in depth. Okay, so here is a simple example, as Raj just mentioned, that it will relax this. So relaxation doesn't necessarily always result in a reduction in the estimate. Okay, but in this case, it does result in a reduction. However, you could have another example. For example, in this particular case, you can clearly see that 5 plus 2 is 7, and the current estimate is already lower than that. So in this case, even though you will relax that particular edge, however, it will not result in a reduction of the estimate. Okay. So that's the whole concept of relaxation, and it's applied on an edge, and you have three different information about that particular edge before you can make that relaxation. So let's take a look at Dijkstra's algorithm, which relies on both the initialization process as well as the relaxation. And so Dijkstra's algorithm will define initially a set S of vertices, and this is important, whose final shortest path weights have been determined. Okay, so S is the set of vertices whose final shortest paths have been determined. Okay, and Q is the rest of the vertices. That's V minus S. And Q is going to be defined, is going to be implemented as a priority queue. Okay, And in Dijkstra's algorithm, the priority queue is going to be different from what we've seen earlier. For example, in Prim's algorithm, where the priority queue keys were different. Okay, in this particular case, we're going to use the shortest path estimates to be the keys. All right. So if you think about this, what are some of the other algorithms that sort of resembles? One of them obviously is Prim's, and any other algorithm that perhaps this might resemble. Okay. How does it actually resemble, and how does it not resemble Prim? So let's talk about that. I've already said a few things, but can somebody further elaborate? What are the commonalities between what we've already said? In Prim's algorithm, remember, we also had a set of vertices, and you had, did we have a priority queue in that case? Come on, getting close to the exam, you should remember this. Okay. So did we have a priority queue in Prim's algorithm? Yeah, no, maybe. Yes, we did, right? We did have a priority queue. However, the priority queue was using a different key. That's it. Okay, so that's the commonality. However, if you think about just when we started graphs, we also did depth first search and breadth first search. Okay, and you might keep one of those two algorithms in mind as you're going forward, and try to see which one of those two algorithms does it resemble more. Okay, is it depth first search or is it breadth first search? And you may already have an idea. Okay, because and we did speak about this. If you're going through a breadth first search versus depth first search, does any one of them, do you think, actually determine the shortest path? Not a tough question. Which one of those, Logan? Yeah. But in special cases, one of those two algorithms can be considered to be actually doing the same thing, finding the shortest path. And which one would it be? Think again. It's only one alternative. So when you're doing a breadth first search, okay, you can think of the edge weights being essentially all the same. So if all the edge weights are 1, and you can simply think of the shortest path being the number of hops to get to a destination, then essentially what you can think of is a breadth first search, traversing the graph in sort of a wave manner. Okay, you're looking at the first wave is looking at the first neighbors. Okay, and it's finding that these are my first neighbors, and then the wave further expands and goes to the second neighbors, and then the third neighbors, and so on. And the rate at which the wave emanating from the source is reaching the vertices is essentially based on the hop count. Okay, if you have 1 hop, 2 hops away, or 3 hops away. Okay, but in this case, it'll be different. In Dijkstra's and shortest path, where you actually have non-equal weights and all the weights are different, then you actually think of it as a wave which is expanding, but it has to reach the ones which are closer in distance as well, which have lower weights first. And you may have some vertices which are multiple hops away, but their overall distance is shorter, and those will be reached first by the wave. Okay, so on. So that's just one way to think about it. So it is similar to Prim's, and as I said, depth first. Okay, did I get that right? Right? Sorry, that was a breadth first search typo. And there, the difference, one of the differences was that in breadth first search we used a FIFO queue. Okay, we didn't use LIFO or stack. Okay, but here we can't really use a FIFO queue because we need to keep track of actual weights. And so just having a first in, first out queue is not going to be sufficient. You actually need to have a priority queue. Okay, and remember, This is what we spoke about, I think, between 210 and 550, that the difference between when you have a FIFO queue, and if you want to convert that into priorities, then you start talking about heaps. Okay. So one of the things that this particular algorithm will assume is that there are no negative weights. Okay. I think you may see some more discussion on this in the tutorial session today with Bryce, where he'll be talking about some of these things. So let's take a look at the Dijkstra's algorithm. Okay, so these are the things that we've already defined. S is a set of vertices whose final shortest path weights have been determined. Q is the rest of the vertices, and they're going to be converted into a priority queue. Okay, and their keys are the shortest path estimates. Okay, and it assumes that there are no negative edges. So the initialization of Dijkstra comprises of the first initialization process itself. Okay, which we've already seen. What that does is it simply sets the estimates to each one of the destinations to be infinity, okay, because you haven't started yet. It sets the parents of each one of the vertices to be nil, so you don't really have a tree yet. And it does set the estimate to the source itself to be 0, okay, because it's kind of obvious. So once lines 1 through 5 are done, we have the following scenario, and now we are showing inside the vertex the estimates as opposed to the delta functions which you saw earlier. Okay, so don't get confused about that. So here, all of these are infinity, and the source estimate is set to 0, and we have a whole bunch of weights given, and this is directly from the book. So and S is then initialized to 0, or null rather. Okay, so this is the null set comprising of all the vertices whose shortest path weights have been determined, which is clearly none. And the rest of the weights are put into a priority queue. Initially, all the values are infinity in the priority queue, so it's a relatively simple procedure, linear in time. And then we're going to insert, so that's what we've done over here. We've inserted all of these vertices into the priority queue. And we saw that because they're all the same, you can do that in linear time. So that's the initialization process. The next step is doing the loop, just like in Prim's algorithm, and let's take a close look at how this is done. So this is the first iteration through this loop, 6 through 12. And we're going to say, well, until the queue becomes empty. So initially the queue is full of all the vertices. Until it's empty, we're going to continue through this loop. We're going to extract the minimum from the priority queue, and we're going to assign it to U. So initially, clearly, the minimum value is the source. Okay, so U becomes the source. And then we do this important step, which is we form a union of U with S. Okay, so this would be using the disjoint sets that we saw earlier. We're going to form a union over here. And initially, of course, the set S will simply comprise of the source. Okay. And then what we're going to do is we will simply look at all the adjacent vertices of U, all right? And we will then relax each one of these edges, okay? So the only two, in this particular example, the only two adjacencies of the source S are T and Y, and we're going to relax them. So, so you can see the same procedure that we just saw a few minutes ago. We're going to say, well, the current estimate is infinity, and if I want to get from S to T, the weight is 10. The weight of S, the estimate of S is 0. So 0 plus 10 is clearly less than infinity. So we will update this to be the new value, which is going to be the sum of these two. Okay, so this becomes 10 and this becomes 5. Okay, fairly straightforward. And then what should we expect next to happen? We're going to go through this loop one more time. And can somebody tell me what's going to happen next? So as we've done the relaxation, we've also done the decrease scheme. Okay, so the priority queue, every time we extract something that's kind of understood by now, is that it immediately makes sure that the heap is kept as a minimum heap. So any thoughts? What's going to happen next? Just to make sure that you guys are thinking along with me. What should happen next? Which vertex are we going to extract next? Q is clearly not empty yet. Okay, we've just extracted the source S from the Q, and the Q has become slightly smaller as shown by this orange tan. All the tan shaded vertices are the ones which are in Q, and all the blue shaded vertices are the ones which are in the set S. Okay, so can somebody tell me which vertex is going to be extracted from the priority queue next, from the min queue? So it's the priority queue is based on the current estimates. All the current estimates are given inside the vertex, okay? And they are 0, 10, infinity, 5, infinity. Yes. Yeah. So why would we extract it? And the simple reason is that it has the lowest key value, which is 5, as compared to 10, infinity, and infinity. It's not going to look at vertex 0, simply because that's not part of the queue. Okay, so we're looking at the priority queue, extracting the minimum out of it. And so we're going to look at 5. And then what are we expected to do next? Can somebody now tell me what should we do with Y, the vertex Y? And again, this is simply following this process. Yes, yes. Okay, you'll have to speak a little louder, but I got through till you're looking at all the vertices of Y, and you're doing the relaxation process on each one of them. And as a result, can you tell me what's going to happen? No, hold on. I just want you to complete the relaxation process. Can you relax each one of the edges? Okay, so Y has at least 3 edges I can see. All right, so 3 adjacent vertices, and you need to relax each one of them. So can you tell me what's going to happen as you relax them? You're going to apply this process, and can you give me the updated values? It doesn't matter which order you do it, you can do it in any order. Yeah. To 8. Yeah, 5 plus 3 is 8. Yeah. Yeah, 5 plus 9, 14. 5 plus 2, 7. That's right. Okay, very good. So can now somebody else tell me what's going to happen next? Well, it's clearly going to do reheapify. Okay, so it's going to make sure that the priority queue is maintained. And next, can somebody else tell me what's going to be what's going to happen in the next loop? Yes. Yeah. So say that again. So you change X's estimate to 13, and after that, anything else that we need to do? Yeah. Is it going to look at all the edges? So it's supposed to look at all the edges, right? So it's also going to look at vertex 0, perhaps. Okay. But you can see that there's no result of that relaxation. Okay. So these are the steps. So we already did this. think we got the right numbers, 7, 4, 8, 14, and then it goes ahead and relaxes to 13, and the rest is fairly straightforward. You can see that now 8 is the min value, and it's going to relax the edges connected to 8, and that's going to result in number 9. Okay, so those are essentially going to be all the updated estimates. Okay, so that's pretty much the entire Dijkstra's algorithm. Okay, it's fairly straightforward algorithm, and as it runs through all of the vertices, eventually you can see that I haven't shown you the dotted Q, but you can see that the tan values are becoming less and less. So the number of vertices in Q is becoming smaller and smaller, right? So eventually at this particular point, the Q, the priority Q becomes null and the algorithm stops, okay? And how do we know what the shortest path tree is? Well, you can simply look at the arrows. So that's sort of embedded in the blue arrows. So you can see that the blue arrow over here is pointing to the parent. So if you reverse the arrow, so Y's parent is essentially S, Z's parent is Y, T's parent is also Y, and X's parent is T. Okay, so this is the shortest path that is formed. Right, so that is a fairly straightforward algorithm, and we've seen this before as well, I think in 210. So far, nothing too new. Question? Right. So let's look at the complexity. This again should be fairly straightforward. And this should remind you of something that we just saw perhaps in the last lecture. So can somebody give me an idea as to what the complexity of the Dijkstra's algorithm will be? And I've sort of given you a few pointers over here. You need to look at the initialization process. You can again think about the complexity of the extract min based on a heap implementation, the decrease, and then how many times are those particular operations being performed in this particular loop. Okay, so think about those again, and can somebody just give me the answer? Yes. Yes, it's assuming the heap implementation, which is so. What exactly was your question? Which line were you referring to? Yeah, so it's not going to be constant time, simply because not only are you going to be extracting the minimum, but you're also going to be making sure that the heap property is kept. Okay, so that's, if you remember it, what that is. Does anybody remember how long it takes to? Yeah, Jack. Log V, yeah. I did get your name right? Okay, good. So that's log V, and again, this is also going to be similar. Yeah, log V. That's simply making sure that if the vertex is changed, okay, so the keys are going to change because the relaxation process is going to change the key, and as soon as you change the key, you've got to make sure that wherever that key is inside that heap, it's not an extract min, but it's making sure that that particular value inside the heap is now in the appropriate location. And that takes, if you remember your heap operations, that again takes log V operation. Okay. If you don't remember that, just review that, and hopefully we'll get to that in subsequent lectures as well. When you take a close look at data structures. Now, the question is, how many times is this entire loop going to perform these two log operations? So while the queue is not empty, yeah. V times, right? Because the queue essentially has all the vertices. Logan? For each vertex in V. Aha, yes. So I got carried away. Okay. This is clearly, as Logan pointed out, is an order of E operation. Okay. So even though you're doing this particular operation, so it's actually a doubly nested loop. Okay. And the question is, and I think we saw this in Prim's algorithm, and I gave you an explanation for that. So if you were thinking about it in a simplistic way, you might say, well, this particular loop is going through V times because that's the number of vertices in the queue, right? And then within it, you've got an operation which is looking at all the adjacencies of every vertex, which again seems to be an order of P, right? So is this an order of V times E? Although I convinced you that this is not an order of V times E when I was discussing Prim. But perhaps we need to take another look at that and convince ourselves once again, why is it not V times E? Logan. Yeah, so there is also a log V, yeah. But I was just looking at the number of times. But number of times each operation. So essentially, you can say that this entire loop is going through V times E times log of V. So that would be a straightforward, simplistic answer. But the question is it really going to take that many operations? Is it really going to be as complex as that? And we did answer this in the last lecture, not too long ago. It wasn't before the spring break, was it? Because I know spring break does tend to cleans up the mind. Somebody else. Want other people to think as well. Why? So do you think this is really going to be V times E times log V? It seems on the surface that it is that complex. So we're taking every vertex out of the heap. We're looking at its adjacent vertices. Okay. So yes. Okay, so what you're saying is that the decrease operation is not going to be as prevalent, right? Simply because it's only going to happen in certain cases, not in all cases. So this particular operation may be reduced. What about the log V operation, the extract min? That clearly, this particular path is clearly V log V. Is that right? Yeah. However, for this additional loop, we seem to be having a reduced number of operations depending on the number of times we are actually doing the actual relaxation operation successfully. Okay. If relax actually decreased V dot D. Right. So now, if you think about it globally, in a sense, we are not going to be doing that too often. And we can sort of do an intuitive response on that rather than doing a very thorough proof. We can sort of see that it will be related to the number of edges. Okay, so if you have a very dense graph, okay, so you may be doing the relaxation process overall in proportional to the number of edges in the entire graph. Okay, so and this is again, it's sort of an intuitive analysis that similar to what Prim had, we come up with an E log V. Okay, and we said why it's not E log E, because log of V and log of E are essentially have the same complexity. So, so hopefully you can convince yourselves that if we do an intuitive analysis, that we can see that the complexity of the most the deeper loop is order of E log V. Okay, but for more thorough analysis, we would have to spend a lot more time on this. Okay, and I'm not sure I haven't double checked on the book as yet on this, but it might be doing more thorough proof. But I'll have to double check that. And this was Prim's analysis. So just for your reference, this is exactly fairly similar, not exactly similar, but we also got a similar analysis done at that point. Okay, both of them E log V. So now let's take at a high-level view of the Bellman-Ford algorithm. Okay, this is quite different from the Dijkstra's algorithm, and it sort of is a brute force approach. Okay, but the advantage of the Bellman-Ford is that it does work with negative edges. Okay, and why does Bellman-Ford work with negative edges, and why does Dijkstra not work with negative edges? We will take a close look at that once we get to the proofs. Okay, but let's take a high-level view of Bellman-Ford algorithm. And essentially what we're saying is that it's a brute force algorithm, and it's going to relax all the edges enough times. Okay, it's almost like taking a sledgehammer and hitting the graph with it. So we're just going to do, we're going to relax all the edges, not once, not twice, but we're going to keep on relaxing all the edges enough times. Now, what do we mean by enough times? Okay, so take a look at this portion of the algorithm, okay, and it's defining what enough is. So can somebody see what we're doing in this algorithm? And can somebody just take a look at that and sort of explain what I've sort of just said in your own words? What are we doing in the Bellman-Ford algorithm? So remember, it's got a couple of loops. Okay, so at the higher level, we're saying I is equal to 1, 2, certain number. Okay, that's what's defining how many times you're going to do relax all the edges, and then it's relaxing for each edge in the entire graph. Okay, in the entire graph, we're going to relax every single edge again and again and again. Okay, how many times are we going to do that? We're going to do that this many times. So, Jack, you had something? Yeah. Okay, very well put. So essentially what Jack is saying is that if we have some graph, right, and if you think about the shortest path tree, the shortest path tree is clearly a tree, and the maximum length of that tree would be G dot B minus 1, right? So the number of edges is essentially going to be equal to this. We've already seen that the number of edges at a minimum in the shortest path, both in the MST as well as the shortest path tree, is going to be limited by V minus 1. Okay, the number of vertices minus 1. So essentially what this algorithm is saying is that let's try to repeat a relaxation process on all the edges. How many times? The number of times that it will, you expect that it will relax the entire tree. Okay, the length of the entire tree itself, okay, the tree that's embedded inside the graph. So we're going to relax all the edges that number of times. That's simply v minus 1. Okay. Now, do you think the order in which you relax the edges should matter? And if you can just try to visualize the graph before we actually look at an example. If you take a random graph, and essentially what you're doing is you this might be the source, all right? And you know, this could be X, this could be Y, and you could have something like this, X, Y, B, Z, whatever. And we're basically saying we're going to relax each one of those edges, and we're going to sort of relax them so that, you know, this gets an estimate, updated estimate, and then this gets an updated estimate, and this gets an updated estimate. And hopefully that will, after we've done v minus 1, exactly v minus 1 iterations of this loop, this will result in a shortest path tree. Okay, so would that work? Would the order in which you're actually doing the relaxation matter? Should you, if you're starting, if this is the source, would it make more sense to relax these edges first? Or what happens if you relax edges which are right at the other end? And would the order work? And I'd like somebody else to also comment. Do you think the order should make a difference at the speed at which we can actually get convergence? Okay, if you start from the wrong edge, from the wrong end, would it take longer to get to the shortest path tree? Or would it matter if we started from the source? And would we get convergence faster? So, Jack. So you just say infinity is infinity less than infinity. Okay, and so it's not going to change anything. So if so this is 10, and these two, and this is initially infinity and infinity over here, and we're trying to relax this particular edge versus we're trying to relax this particular edge. One of them is going to be more useful, right? If we try to relax Y and Z initially, well, it's simply going to say, well, my estimate to get to Y is infinity, my estimate to get to Z is infinity, and the path is, 20, all right? So is 20 plus infinity less than infinity? Well, no, right? So infinity that's, it's one of those questions that kind of hard to answer, but it's not going to do any relaxation, okay? Because it's not going to say, well, now this is infinity plus 20 versus something else, right? So it's not going to have any impact. Versus if you did a relaxation over here, and you know that the estimate is 0, and the current estimate over here is infinity, and this is, let's say, a distance of 5, then this is clearly going to have a much more useful impact in terms of relaxation. Okay, so the order should seem to matter, right? The other question is that if you did it in the wrong order, can we convince ourselves that we're going to get the shortest path weights on the graph in this many times if we simply do it v minus 1 times? So in other words, let's say we have this particular graph which has got v is equal to 1, 2, 3, 4, and 5. So basically you're saying 5 minus 1. If we do a relaxation 4 times on this particular graph, then regardless, and this here is not specifying the order, okay? So it's basically saying that regardless of the order in which you do the relaxation, if we apply relaxation once on all the edges, then repeat the whole process again twice, thrice, and 4 times. After 4 times, we guaranteed this, at least Bellman-Ford is claiming that we will be guaranteed unless there are certain cases, we are guaranteed to get shortest path weights. Yeah. Okay, very good. So essentially what you're sort of going towards is the proof of Bellman-Ford, okay? And that we will do in a more rigorous way, okay? So the correctness proof is important, and to do that correctly is important. So yes, the answer is that it is guaranteed, and an induction proof will be able to show that, yes, you only need to do, if you have V vertices, 5 vertices, you only need to relax all the edges 4 times, regardless of the order, and you will be sure to get shortest path weights. Okay. So let's see how this applies. There is one more aspect to it, which of course is very important difference between Bellman-Ford and Dijkstra, which is that, the whole reason why we're doing something which is a sledgehammer approach or brute force approach is that we want to be able to avoid certain issues. Yes. Okay, so seems to be dying again. And we don't have any extra batteries, as usual. So I'll just speak louder. So again, if we're trying to relax an edge out here, and remember, we start with a particular source, right? And we're trying to find the shortest path from the source to all the vertices. And we're doing a series of relaxations. And the relaxation basically says that initially, all the estimates are infinite. All right, all of these estimates are infinite except for the source, which is initially set to 0. And the relaxation between, let's say if you're trying to relax y and z, it's going to say, well, is my current estimate to y, which is infinity, plus the distance from y to z, which is 20, will that improve the current estimate to get to z, which is also infinity? Okay, and we're basically saying that it's not going to end up in anything useful because we have infinity on both sides. Versus if we try to relax the edge s to y, okay, s has a current estimate of 0. The cost of going from s to y is 5. All right, so 0 plus 5 is clearly less than the current estimate to get to y, which is infinity. So now infinity is going to be replaced with the value of 5, which will be the new estimate to get to y from the source. Okay, so that basically what we are saying is that that seems to have a positive result. Okay, we've actually reduced, we found something which actually had a useful result, right? So we found a way to get to y, which was less than infinity. Versus if we did a relaxation on 2 edges, we don't have any clue as to how to get there, okay? And currently the estimates are already infinity. So if you relax those 2 edges, you're not going to get anything useful out of that. So that's a good question. What do you think? We haven't answered that question. In a practical scenario, so we're doing 2 things. We're doing complexity analysis, right? Which basically says what's the worst case, right? And then the more practical approach is if you take some real world scenario and you actually try to see how long it takes, is actual time differing, right? As opposed to the complexity, which may be the same. So what do you think is the actual time if we start from the source and go to the other side versus if we work from the other edges and go to the source? Which one is actually going to be faster in terms of convergence? I think your intuition is probably going to help you over here. What do you say? So yeah. So in practice, if you go from the source and you can check it out as well, you will hopefully get fewer steps. But what Bellman-Ford is basically saying is that we're guaranteeing that regardless of which order you pick the edges, you're going to have an upper limit. Okay, and you can guarantee that particular upper limit. And the question now is, again, we'll get to that in a few minutes as to what is the upper limit. Okay, and you can just answer that right away initially as well right now. So if you look at this particular complexity, what is the actual complexity of the 2 to 4 loop? You've got nested loop. Okay, so we're doing V, and then we're doing all the edges, regardless of whether in the previous case we said, well, if the relaxation actually decreases the destination estimate, then we're going to update the priority queue. But here we're not dealing with any priority queues. Okay, we're just doing a relaxation process. So what do you think is the actual complexity of this loop, this nested loop? Shouldn't be too difficult. For I is equal to 1 to V, right, Logan? Say that again. Yeah. So it's going to be order of V times order of E, right? Simply because this loop is executing exactly V minus 1 time, which is order of V, okay? And the other loop is repeating itself exactly E times, okay? So it's simply V times E. So this is an order of V times E, or theta of V times E, okay? So it's quite a lot more complex. If you think about the Dijkstra's algorithm, which was E log V, E log V as compared to E times V, okay? Significantly different, a log operation different. So now let's take an example of this. Now, as I said, there is an important aspect to the Bellman-Ford, which is that it is able to determine whether you have a negative weight cycle. Okay. Now remember, we looked at negative weight cycles. This was our earlier slide where we said, well, if you think about updating, this was the example that we saw, that if you think about these particular cycles over here, all right, and you think about whether you can actually have a negative weight cycle, then you can sort of go around that particular cycle infinite times, and you can keep on reducing your cost. Okay, so that is the example where you take on an Uber ride and you forget about going to your destination. Okay, and you just keep on making money over here. So in those cases, what's the shortest path going to be? Well, we saw that earlier is that it's actually going to be infinity. Okay, and that's not very useful. So at some point, if we have a negative weight cycle, what do you want to do? If you're doing relaxations, does it really benefit us to keep on doing this relaxation around this particular loop? So if, for example, you had Dijkstra working over here, okay, and you had a negative weight cycle, what would happen? Well, Dijkstra would basically say, well, I'm going to update this destination cost, and then it's going to go in a cycle and it's going to keep on updating the cost, okay? And you can look at the specific example in more detail, but let's just try to understand that it's going to keep on going down a sort of a rabbit hole, okay? And that needs to be stopped. So there is a simple way to stop that, and here it is. So it's going to detect negative weight cycles in a very simple manner, okay? So it's basically saying after you've completed the loop 2 through 4, we're going to essentially have convergence, okay? And we're going to have all the estimates to be equal to the actual path weights, okay? And once that is done, we're going to do one more check, okay? We're going to do one more round of this inner loop, okay? So we're actually going to do V minus 1 loops over here, plus one more loop. So it's actually going to be a total of V iterations of relaxations, okay? And the last round of relaxations of all the edges is simply going to do one check, okay? It's going to check for every edge whether the relaxation actually resulted in something, okay, whether the relaxation actually resulted in the destination being reduced. Now, think about what impact that's going to have on this on a negative weight cycle. Okay, in a negative weight cycle, after you've done V minus 1 of these iterations, it should have converged. But if there's a negative weight cycle, it's not going to converge. Okay, and if it's not going to converge, then you're going to continue going down that particular abyss. Okay, so you're going to keep on reducing the weights, the estimates continuously. Okay, so Bellman-Ford basically says that we're going to just check once after V minus 1 iterations, and if that one particular operation resulted in even a single relaxation which was successfully done, then we're just going to stop. And we're going to say, well, now we know that there is a negative weight cycle. Okay, yeah, Jack. This one here, or the previous one here? Yeah. Yeah, you don't have a negative weight cycle. So are you talking about Bellman-Ford algorithm or the Dijkstra's? Bellman-Ford? So it shouldn't. It shouldn't, but you can check it out in more detail. If you have negative cycles, it shouldn't matter. The order shouldn't matter. Okay, but if you want, you can double check that. So essentially, what we've said is that Bellman-Ford has brute force approach. It says, well, we're going to relax a certain number of times after that, and that will be shown in the proof of correctness that we will be guaranteed if there are no negative weight cycles, then loop 2 through 4 will ensure that you have solution. However, if you do have a negative weight cycle which is reachable from the source, then you will have the following result. You will have a false result. So it's not going to solve the problem. It's simply going to stop and say, well, there is a problem with this. I can't find the shortest path weights because it doesn't exist. Okay, because you have a sort of a black hole in the graph where if you go in there, you're just going to go in and get to negative infinity. Okay, so it's just going to stop and it's going to return a false. Otherwise, if you don't have a negative weight cycle, then it's going to return a true, and it's going to return the parent edges, and that's going to be your shortest path tree. Okay. So now let's take a look at an example of that and see whether that works. So here's Bellman-Ford being applied to a slightly different graph where you have a whole bunch of negative edges. Okay. And the initialization process is, of course, going to be the same. So we're going to do line 1, which is done exactly the same way in Dijkstra. So we're going to set the distance estimates to be infinity for all the vertices except for the source vertex. And we don't have a priority queue in this case. Okay. So in some ways, it is simpler, perhaps to implement, but not in terms of complexity. After line 1, this is what we're going to have. After the first loop, it's showing one particular result. Okay. Now, can you guess what the order of relaxation of the edges was in this particular case? It's given in the book, but I haven't copied over here. I don't know the actual order as well, but I can guess what it wasn't. So can somebody guess after the first loop, which order was not followed or which order could have been followed? So we're relaxing all the edges, right? We're just relaxing them once. And so just think about some order and see whether you get this particular result. So it's basically saying that these two estimates have been updated from infinity to have been relaxed. These two edges have been relaxed, 6 and 7, but some of these have not. Okay, so can somebody venture to guess what was the order in which the edges was or wasn't relaxed? I want somebody else to be, I don't want Jack to be doing thinking for the rest of the class, or Logan for that matter, or Yuvraj for that matter. Yes. Yeah, because this is just one iteration. And if you had started from the left, then what would have happened? Because if, let's say, you had done this relaxation first, and you had the new update for t being 6, and then you had relaxed this particular edge, then it would have said, well, 6 plus 5 is 11, and so this would have been changed to 11 in the first iteration. And that would be sort of the smart way to do it. Okay, just going back to your thought earlier, that if you started from the left, it would be faster. But since the book CLRS chose a different order, it chose, going from this direction. So clearly, initially, the weights were not. So let's say if we initially updated this, but you initially relaxed this particular edge, you would say infinity plus 5, is that less than infinity? No, so this will remain infinity, and so on. And these are not updated. And essentially what it's saying is that, my guess is that the edges ST and SY were the last to be done. Okay, if they were not the last to be done, then at least some of the other vertices would have had an update as well. Okay, so if these two were the last to be done, then the updated estimates had no impact on any of the other estimates. Yes. I would guess it's random. Okay, so because if you really wanted to be smart about it and you knew what the source is, but then you would have to have a lot of information, additional information about the graph to be able to go as to which direction you want to go. And that would make the algorithm a little bit more complex, but it might in practice help. So if you were actually implementing Bellman-Ford in your company, and you said to your boss that it doesn't really matter which order I'm going in, your boss may not be too happy, because he said, well, I know that the complexity is E times V, but in practice, I would like to see if it can be do it faster. The two algorithms may have the same complexity, but one may be better than the other. So you could actually come up with a better algorithm, which actually looks at the source and says, well, if I use this and I don't increase the complexity that much, I can actually achieve a slight modification of Bellman-Ford, which is actually better. Okay, and I'm sure there are algorithms like that, but that's up to you guys to actually discover those as well. Okay, so that was the first loop. Now we take a look at the second loop, right? And so in the second loop, we can see, well, why don't you give it a shot? Well, it depends on which order you do it. So let's not make it complicated. You can see that once these two are updated, then even if you did a different order of things, you would get, depending on which order you did the relaxation, you would get a particular set of results. Okay. But what is important is that it does, after 4 iterations of relaxations, because it has 5 vertices, so we did 4 iterations, it did result in something. Okay. And now my question is, when we go for the final true or false question, what do you think it returns? And you'll have to take a sort of a look at this and see whether should it return a true or false in the final stage when you're executing lines 5 through 7. So remember, it's basically saying that if there is a negative weight cycle, and it's going to basically detect that by checking if after this stage there was an edge which was relaxed, successfully, meaning that the destination estimate was reduced, then you have a negative weight cycle. So without thinking about the negative weight cycle, because that's easier to detect, but just think about whether any of those edges can be successfully relaxed in stage E. So, just pick some edges and see would those, somebody want to pick an edge and see whether that results in a relaxation? Everybody's still relaxed. That was a joke. So let's take a look at Z and 0S. What happens if you relax this particular edge? What are you going to get? You're going to say, well, is -2 plus 2 greater than 0 or less than 0? Well, it's not, okay? So you can't really see any particular edge which is going to result in a successful relaxation. And by that, I mean that the estimates are going to be reduced. So the answer is true, that it's actually found the shortest path tree. All right. So that was a quick review of Bellman-Ford, and we do have a few more minutes left. What do you know? So let's take a look at the complexity. This is something that we've already seen before. So to show you the results, we can simply see that this is V times E. Okay, the others are simpler. So this is simply a single iteration. That's order of E. The actual initialization is simply order of V because you're simply doing a relaxation for all of the vertices. And so this is pretty bad. Okay, so Bellman-Ford is not your first choice of algorithms, especially if you don't have the issue of negative weight cycles. Okay, but even if you have negative weights, regardless of having negative weight cycles, unfortunately, Dijkstra does not work. Okay, we haven't seen an example of that, but we will hopefully take a look at that in the coming lectures. We have about 5 minutes left. Let me just start you on the proof of correctness, and we will take a closer look at this in the coming lectures. So here's the first lemma, okay, and this is called the triangle inequality. Okay, basically says that for any edge u comma v, all right, so let's say this is an edge u and v, all right, we have the following property, that the shortest path weight going from S to V, okay, so this is the shortest path weight, okay, which means somehow you magically know what the shortest path weight is to get to V, then this is going to be always less than equal to the shortest path weight to get to U, assuming again that we know that, okay, that we know somehow we know what delta SU is, and we somehow know what delta SV is. Then you're saying that delta SV is always going to be less than delta SU, which is some other vertex, and then taking U to V, okay, and then adding this on. And can somebody try to rationalize that and tell me, why does that make sense? Why does the triangle inequality make sense? How can we just say that delta SV is always going to be less than equal to delta SU plus the weight going from U to V? Again, somebody else. You can keep your hand up. But yes. Okay, that is a good point, and let's see if that is relevant over here or not. That is sort of going back to geometry, okay? And that's, I'm making an assumption that we're working in a two-dimensional surface, and this is a triangle as we know it. And in a triangle, the sum of these two edges is actually going to be longer than this particular edge. Okay, if this particular if this is, let's say, S, and this is U, and this is V, and if U is not directly in the line between S and U, S and V, then if you make it into a proper triangle rather than into a single line, then these two are going to be longer. That's absolutely true. And this sort of has a resemblance to what we're trying to do over here, but not necessarily. Okay, but you have, you're thinking along in the right direction. The gentleman in the back, all the way in the back, behind Jack. Yeah. Did you have your hand raised, or somebody had their hand raised? Whoever was behind Jack. Nobody? I mistook a hand. Maybe somebody was just stretching. So any thoughts as to why? So now think about the definition. So we're saying delta is the shortest path. So just think about that definition. If delta SV is the shortest path, can you have another shortest path, which is sort of thinking along the triangle lines, that is going perhaps through a longer path, and then yet it's claiming to be shorter than the original path? Jack? Yes, so that's a very good point. So we are assuming that we don't have negative weight cycles. Okay. Exactly. And so this goes back to one of the cut and paste proofs that we had earlier, right? We said that if this particular path was actually shorter, then by definition of delta, it's a contradiction in definition. Okay, but let me retract my answer to what I just said. The question is, what happens when W is negative? Would this still be true if W is negative? And we just have a minute to think about it. And yeah, what do you think? Somebody else, Yuvraj. Yeah, it's a contradiction in terms, you see. Even if W was negative, that would still not be possible. Okay, so essentially, if the above was not true, then delta SV would not be the shortest path. Okay, so it's sort of a contradiction in terms. So this was one of the simpler properties. We'll look at more of these properties in the next lecture. So good luck with your exam.